SwayamPrabha. Digital India. Educated India.
Heterogeneous reactions we have been talking. Heterogeneous reactions, yesterday we started this, and as I told you, I just want to give one or two examples so that you will know what is the difference between heterogeneous reaction and homogeneous reaction, and we go deeper into homogeneous reactions because that is needed for this reactor theory course. Okay. So, in heterogeneous reactions, yesterday we discussed about catalytic and non-catalytic. Okay. So, the idea here is that how do we develop a rate equation for heterogeneous reaction if it is a catalytic reaction, and also non-catalytic reaction, the rate, how do you develop for non-catalytic reaction. So, that is the idea. So, we have taken catalytic example as ammonia, right. Catalytic reaction, ammonia synthesis. That is what is the example what we have taken, and this ammonia synthesis, as we know already, there is not a new process, that is an old process. So, we have taken a packed bed. Okay. So, then this is coming out, this is entering somewhere here. I have taken for my kinetic equations. Okay, I have to take a single particle. This is true, even if I conduct this ammonia synthesis, catalyst as iron, right, fluidized bed also I can take. In fluidized bed, these particles will not be stationary, not like packed, they will be moving. Yesterday also I have demonstrated how the particles move. So, they will be moving. So, even when they are moving, I can pull out one particle. What is happening around that particle? This is the original system. So, for all heterogeneous systems, you should have that thinking of some thinking about the process. If it is fluidized bed, okay, so what is happening? Particles are constant. Around that you have the flow of reactants. Okay. So, then what are the steps that are required, right? That we understand. Fluidized bed also now we understand. Fluidized bed will be something like this, where gases are entering, gas, liquid also can be same. So, here are the particles, this is the catalyst, and then it comes out. This is fluidized bed. So, when we are making these particles float with the support of the liquid or gas, you are able to follow me, for fluidized bed, because most of the chemical engineers must know what is a fluidized bed, right. I think Arya, in your wastewater treatment also fluidized beds are widely used, right. So, I think in chemistry they may not be 100% knowing that, I think someone has to help them. So, you take this for example sand, because it is easy to imagine. Sand all of you would have seen, I think, do not tell me that you have never seen sand. Okay, yeah, you have seen sand, no? Yeah, okay. So, sand you just take in a cylindrical column where you have a distributor plate at the bottom, okay, and now send the air. For example, air you cannot see, but we know, we can feel, right. When you put fan starting, air is touching you, but you cannot see it, right. Yeah. So, then you are sending air or some other fluid also, but air is easy for us to imagination. This air, when it is going through the perforations, it will push the particles, and then it also moves through the particles to go, right. If I am using very small flow rates, then air has just the capacity to move through the particles, and now slowly increase that velocity. I am just telling particularly for this chemistry people and those who have not been exposed to that. So, slowly I am increasing that flow rate here through this. Before that you have sand just filled up in that. That is theoretically a packed bed. Why packed bed? That is a packed bed because particles are not moving. Then slowly introduce the air. Then at very low velocities, those the gas will go through the perforations and also through the particles, between the particles, not through the particles, means not inside the particle, okay, around the particle, and we have in a packed bed the what is called void edge porosity of the particle of the bed. So, through that it goes. So, you keep on increasing the flow rate a little bit by little bit. So, initially when it is very small, then it will only move through the particles, but when it has sufficient velocity, then it starts moving the particles. That is the first time. Okay. So, that means the particles will try to get adjusted on its own when the when there is a such a velocity where it is able to move the particles a little bit. You slightly increase even above that, then the entire particles also will be floating. And when I look at one particular particle, then this gas is sufficient, the gas velocity is sufficient to keep that particle under suspension. Okay. Theoretically, you can also be fluidized if you are going by a motorbike very high speed, correct, no? Because what is happening is the drag force of the air which is acting on your body, right. If you have not properly hold it and then legs are not firmly on the pedals, then you may be fluidizing. That is what I am telling. Or afterwards you may be pneumatically conveying. That means you will travel with the air. Okay, that is also same thing happens here. Sometimes you float and afterwards you will be travelled. So, here also all these particles are just suspended in air stream. Okay. That we have lot of dust is there now in the air, you can see that, no? On your cycle, or if you have car, or if you have your furniture and all that, and if your room is open, the windows are open, then you can see after one day you go and touch it, there is a lot of dust. So, those particles also practically fluidizing, right, if they are not moving from place to place. When it is moving from place to place, then they are also pneumatically conveyed, and finally it will go, and then it unfortunate that it will enter your room, because there is no sufficient amount of breeze there to go away. So, then they settle down. Okay. So, that is what we are talking, and even this catalytic reaction, the solid particles are catalysts, and the gas which I am telling here is ammonia plus, not ammonia, hydrogen plus nitrogen together mixture. Okay. You may send it in stoichiometric quantities or whatever. Okay. So, that is the one what you are talking. Even here I can simply pull out a particle. Not only this, we also have what are called rotary kilns. Have you heard of them? It is a kiln, big tube, cylindrical tube, it will be slowly moving. You put now this side the solid particles, right, and opposite side you can also put oxygen and hydrogen. The particles may be slowly coming, and you are taking back again introducing them, you take back and again introducing them. That is also a possibility, no one does that. Okay. But that is also a possibility. Why? All these things are possibilities, but these are difficult possibilities than packed bed. Packed bed is the simplest. This also can be used. There is another reactor also called moving bed reactor. You take the packed bed and put a hole here, not distributor. Distributor has small holes where the particles cannot fall, only air can enter, or nitrogen and hydrogen can enter. So, now you can put big holes there where the solids can slowly come down. So, then you are also sending in the opposite direction the gas. Now, the entire bed is moving, that is why it is called moving bed. Okay, understood, no? These are not generally difficult. Okay. So, that moving bed also, when I want to develop a rate expression for catalytic reactions, I will pull out one particle again there, right. See, the chemical reaction rate will not change in all these systems. What will change is the physical rates, that means how mass is transferred to the surface. But in all these things, what is our imagination? We have a particle. Okay. Yesterday I have drawn horizontally, but now I will so more truly I will just draw this. So, this is how, if I pulled out, because I pulled out one particle. Why I should pull out one particle? Because let me imagine that what is happening in this one particle, same thing must be happening to all the particles. So, if I develop this equation, and this equation is valid at any point where you pulled out, and because it is a packed bed, there is a change of concentration from this place to this place, then I can integrate, because this is a distributed parameter system. That means the concentration is changing from this end to this end, whereas here it may not. I mean that better not talk now about fluidized bed. Fluidized bed is one of the most difficult reactors to be modeled, to be constructed, to be to operate also. It is not that easy, but still very efficient one. But why it is efficient also I will discuss if you take the course next semester, but right now I think we will just only mention the names. Okay, good. So that is why in all these systems, whatever reactor you choose, whatever system because we have many possibilities for the reactors, heterogeneous systems. So now if you see this particular bed, right, there are two phases, and in our diagram we have contacting pattern, right. So now we have to talk about for each phase what is the contacting pattern. When you are talking about homogeneous reaction, there is a single phase. So you are only talking about contacting pattern of that particular phase, whether it is in perfect mixing or whether it is perfect plug flow or whether it is in third one. Perfect mixing is mixed flow. Pooja, plug flow already we told. Don't forget batch, I say. It may be LKG information, but still, because that is what first we learned, batch. So we have only three contacting patterns, whether it is batch or plug flow or mixed flow. Plug flow, mixed flow are continuous, okay, and whereas batch. But you have to now identify for each phase here how they are moving. That is very important again for us. So when I talk about this packed bed, I have solid phase and gas phase. These two, no, non-catalytic gas solid reaction. So now I have to tell what is the contacting pattern for solid in packed bed. We have only three. Just imagine, I say we have only three: batch, plug flow, mixed flow. Batch. Why? Because solids are not moving, they are there. Okay. So that is why. So this is batch. And what about gas? How it is moving? It is plug flow. Why? I can tell. I mean, when you look at the packed bed, fluid mechanically also you can prove that most of the time your plug flow, the velocity profile will be flat. If you are operating properly with Reynolds number, no book gives about the connection between Reynolds number and plug flow. Only KK gives. Okay, that connection. That's why please remember, when you are operating packed bed, it should be in the turbulent Reynolds numbers. What is the turbulent that Reynolds number for turbulence in a packed bed? Greater than 500. Don't tell for 40,000 and all that. 40,000 also will be, but I think starts from 500 onwards. Okay, good, excellent. You remember that. Yeah, so that is why here you have plug flow PF. Now my design expression will depend on whether I am choosing solids or whether I am choosing gas. And here I can't choose solids because they are not. That is not the phase where the catalyst is converted from one to the other. We are only talking about in the reactor conversion from reactant to products. Only gas is converted from reactants to products, whereas catalyst here only helps me in increasing that rate of reaction, right. So that is why that even though it is batch, I cannot write any equation for a catalyst particle, because as far as conversion is concerned, because the reaction is taking place only within the